Okay, before I start on the capacitive load, I want you guys to go back to the beginning of your notes for the AC circuits. And remember that both the voltage and the current have a sine function inside of them, okay? The voltage was given as a sine omega dt, and then the current was given as a sine of omega dt plus phi. That's going to be important. We're going to define that phase constant here in a couple minutes. Okay, so here I've got a capacitive load. I have an AC source, and then I have a single capacitor. That capacitor is going to have some voltage across the capacitance, okay? That voltage across the capacitance is going to be equal to some maximum amount of voltage across the capacitor times the sine of omega dt, okay? So we're defining the voltage across this capacitor as some maximum amount of voltage, an amplitude of voltage, sine of omega dt, okay? Now here's where it gets a little hinky. We first remind ourselves that the charge on a capacitor is equal to the capacitance multiplied by the voltage across the capacitor. Charge of the capacitor is equal to capacitance times the voltage of the capacitor. So now I'm going to rewrite this as C, capital VC, sine of omega dt. So I've replaced this voltage across the capacitor with this guy right here, the amplitude of that voltage multiplied by the sine of omega dt. Now here's where the problem comes in. In order to define the current that is going through this circuit, I need to take the time derivative of the take the time derivative of the charge. So the current across the capacitor inside this circuit is going to be equal to the time derivative of the charge. So I take the time derivative of the charge. Now notice here, I'm going to take the time derivative of the charge across the capacitor. The sine function is going to turn into the cosine function. And the omega d is going to come out. So now I'm going to have something that looks a little messy. I'm going to have IC is equal to omega d c capital VC cosine of omega d t. Okay, I know it got a little messy. We take the time derivative inside here. C and VC are still there. We got an omega d came outside because we took the derivative of what's inside here. And now the sine function has turned into the cosine function. Okay. Now we want this to look similar to what we did for the resistive load, and there's a reason why we're doing this in a couple of minutes. We want to treat this similar to a resistor. So I know it seems weird, but we're going to try to think about that capacitor as like a resistor. In order to do that, we're going to define a new term. That new term is chi, that's a capital X. Chi is equal to 1 over omega d. I'm going to erase that real quick because that became a total mess. 1 over omega d times c. Okay? The driving frequency multiplied by the capacitance. This is known as capacitive reactance. This right here, capacitive reactance. We are treating the capacitor similar to a resistor. Okay? Now we've got a little bit of a problem here. We've got a little bit of a problem. What we now have is we have the current across the circuit is equal to VC over chi c sine of omega dt. But then I know that it has to look similar to what we defined at the beginning of the chapter as capital IC sine of omega dt minus phi. Okay, so I haven't finished writing what's right here. Okay? So in order to make this thing look better, I've got a cosine here, I've got a sine inside of here. So in order to transform the cosine into a sine function, what I'm going to actually do is I'm going to subtract 90 degrees. So I'm going to subtract 90, so the minus minus becomes plus, and now I have a phase constant of 90 degrees. So this phase constant is equal to negative 90 degrees. The reason why I had to do that again, Here is what it should be, sine of omega dt minus 5. But over here, make sure to include my parentheses there. That's bad notation. Make sure to include my parentheses. But here I have a cosine term. I want the cosine to look like the sine term. So in order to do that, I'm going to subtract 90 degrees from this sucker. Okay? Got a bit of a mess here, so I'm going to let you guys pause. Make sure you got this in your notes. Okay. Now we wrap it all up. So I've got VC over chi C is equal to IC. So the voltage across the capacitor divided by the capacitive reactance. Again, we're treating it like Ohm's law. We're treating this chi term like a resistor. Okay? And now I get that the voltage across the capacitance is equal to IC multiplied by chi C. So again, it looks similar. It looks similar to V equals IR because we're treating the capacitor like a resistor. Okay? Now I'm going to pause here. We're going to go on to the inductive load in a second, and then we're going to bring everything together in one final video. Okay? I know, this is a little complicated. I highly recommend looking at those diagrams in the book that relate the sine and cosine functions.